Raising the bar, or energy level? Today we will talk about the next section as we move on from the infinite square well onto the harmonic oscillator. There's a lot to be discussed in this section, so we will look at two methods of handling this style of potential. And in this first method, they call it the algebraic method, which uses the raising and lowering operators, also known as the ladder operators. And here, for our question, we want, for the harmonic oscillator, construct the psi sub 2 of x, which is the second excited state. We want to sketch the ground state, first excited state, and second excited state, and check the orthogonality of the ground state, the first excited state, and the second excited state by explicit integration. Okay, so within using these operator methods, what we have to understand here is that this potential is different from the other ones we've seen because it has a ground state level that's accessible, and we call that psi sub 0. Here, since we were trying to get to the second excited state, or psi sub 2, we know that n equals 2 in this construction. So using the general form of finding the excited state from the state below it, starting at the ground state, psi sub 0, we have a normalization of 1 over the square root of n factorial, and then we have this thing in parentheses, which we know is an operator due to the hat notation, and we call it the raising operator because of this plus sign here. We're trying to raise this ground state up to an excited state psi n. And since we want to get to the second state, this is n up here, which apparently is just a copy paste error. Anyways, that's supposed to be n to let you know how many times you apply the raising operator on the ground state. And so we have this nice compact form, and now we need to kind of expand it and start operating away. So to get to psi 2, or n equals 2, we plug 2 in everywhere. The 2 factorial and the 2 up here lets us know we're applying the operator twice. Not just squaring it like we would with the number, but applying it twice. And so here, I have to be careful to note that I have a plus operating on a plus operating on psi naught. So this operates on the results of this parentheses. And why do we have to be careful of that? Well, in the operator sense, the operator itself is defined as something, a constant, with a momentum operator and a position operator. The goal here was to try to factor the Hamiltonian, which we know could be written as momentum and spatial operators. However, there's a little weirdness in the fact that things don't commute because momentum is actually defined as a derivative, as we see here. I, h bar, negative of course, d by dx in a one-dimensional case. So what we're doing here is we have to color code it out so we know that the red is what we see from the operator acting on the blue, which is the ground state wave function. So here you see we have m omega pi h bar to the 1/4. That's the normalization of the ground state, which gets carried through. And we see that we have e to the minus m omega over 2 h bar to the negative x squared. And again, we've seen this before. This is a typical Gaussian exponential. So at least we've seen it. We know how to work with it. Now we just have to tidy this thing up, and we see that we get the 1 over square root here out front. But we get the parentheses in blue out front. All of those are constants. We don't need to worry about it. We can clearly see here what the operators are meant, and the fact that we have d by dx, that needs to act on this blue function, which is a function of x. So such as multiplication, we actually have to do something with it, and that's why it is an operator. I'll go ahead and note here that the double negative I here leads us with the negative 1. So that's I squared is negative 1. So that's what we will see on the next page. Well, as promised, we reduced that double negative I down to a negative 1. We distributed the function so each operator can act on it independently. Here we have the momentum operator, d by dx, acting on it, and the position operator, x times the blue function, blue exponential. You see here we don't have much to worry about on the x side, but we do have a derivative to take, which leads us to a chain rule, and that leads us to a coefficient mess here of negative m omega over 2 h bar times the derivative of x squared, which is 2x. But notice that with exponentials, I get the same thing out, just with the chain rule of the argument, so I'm able to factor the exponential term to the right, and now I can clean up the bracket. Noting here that my negative h bar cancels with the negative here from the exponential, and the h bar there in the denominator of the exponential, and then my 2 here cancels with the 2 from the x squared derivative, and so I'm able to tidy this whole bracket up because I have now 2 copies of the m omega x as we see here. Okay, now of course we can take the 2mx or 2m omega, bring it out front, which is what we do here because those are constants with respect to the variables x and x squared. And of course we have to raise this function again by another operator, so we have to apply the momentum operator and the position operator acting on the combined functions of x and the exponential. When we do that and distribute everything, we see that the constant come in here again, gets rid of the square root, so we have a 2 h bar m omega instead of a square root there. We have 2 sets of that constant, and thankfully it cancels away nicely to a lot of things, so we can reduce it. But let's note here that the momentum operator, once we distribute in this product of a function here, that will lead to our product rule with the derivative, and here we just get, another scaling factor of x onto the exponential. So let's see how we clean that up. So then cleaning up this initial constant out front, much tidier here. We see, as promised, that we have a product rule with that derivative acting on x and the exponential. Derivative of the first, leave the second alone, plus the derivative of plus leave the first alone, take the derivative of the second, chain rule it out. You see we get some cancellation of 2's again. And here we're just left with the x operator acting on x, and that's just a straight multiplication. Again, every term in here has that blue exponential, so we factor it out. Always, always, always. Sometimes shorthand will start to take over, and we won't even put that in there. We'll just put the coefficients in there. That can be sloppy, so be aware of it. And then here, I want to factor out this h bar here, so we're going to have to put one under the m omega x squared term because we're force factoring it. And what we see here is kind of a nice surprise. The h bars cancel in the constant term out front, and we get to conjoin the x squared terms, which, since they both have the same coefficient of m omega over h bar, so we're able to tidy this whole thing up into something nice and compact. The 1 over root 2, that was a normalization requirement of the general form for the nth state generating function for these operators. This is the ground state normalization. These are the polynomials from the operations. So we have to use these to get to the second state, and that's what makes it different from the ground state. And of course the exponential, which is just a solution to the time-independent Schrodinger equation for the case of n equals 0. Note here that aside from the constants, we're starting to get a polynomial built on the coefficient of the exponential. Be aware, when we get to another heftier method, or potentially heftier, with the Hermite polynomials, these polynomial figures here will come back again, and I promise you it's going to look gross, so at least you have a chance to see it now. Well, now that we have that second excited state, and we found the first excited state on our way there, let's go ahead and take a look at the graphs that these things produce. The functions written out in plain text, the ground state in blue, we've seen that, nice and neat. Although we didn't explicitly clean it up, we saw that the psi1, the first excited state, had a multiple of x on it, same parentheses constant, same exponential, and this was that tidied up square root from the raising operator and the derivative. Now that I have this psi1, I created psi2, and we just saw how that cleaned up. I would like to note that this is even because the Gaussian, as we see here, up, down, symmetric about the y-axis, good there. This x multiplying to psi1 creates an odd solution, As you see here, we're positive to the right, negative to the left. So we're anti-symmetric about the y-axis, which again was one of the theorems we posted about to start off this chapter. And then here we have an x squared leading term and then a 1, which is just a constant. So this is even, that's even. And so multiplying two evens gives us an even. And as you see here, the graph supports that, where we have a dip this time below at 0 because of this -1, of course. And here we see again we're still symmetric about the y-axis. And we go through all this detail to say that, look, what we're going to do next with orthogonality, making use of these even-odd properties, is going to save us a ton of time. Why not use our intrinsic understanding of even and odd to help us facilitate these integrals? And so let's go take a look. What we're seeing here now is the orthogonality condition. Really, this is the orthonormality condition, which takes into account the normalization and the orthogonality due to the Kronecker delta, which is what we see here. This states that this integral is 1 when m equals n, and 0 for m not equal to n. And if the left-hand side of this integral doesn't equal 1 for the same m and n, which in this case we're not asked to check, we're just asked to check to make sure that the integral is equal to 0 for the odd pair, for the index pairings that aren't the same. Get used to that integral. It's going to come up again, especially in the formalism, so be aware. Now back to the point of even and odd, we know that since the ground state for 0 is even and the first excited state is odd, the combination thereof gives us an odd integrand over even symmetric limits, and that of course yields a zero integral. So the same argument can apply for the second excited state acting on the first excited, or multiplied with the first excited state. Again, we get an odd integrand over symmetric bounds, so that's 0. These geometric intuitions clearly saved us a lot of time. The one that we're left with is the case of even times even, because that comes out to be even, okay, which is useful here, and we'll try to clean it up. We saw that the purple had a bunch of constants that needed to be recognized, but both of them had an e to the x, and both of them had this parentheses m omega pi, or m omega over pi h bar. So here I just combine them to save space with a 1/4 plus a 1/4 when you're multiplying. Same thing with the exponentials here. We just combine them so we get a factor of 2 there, and that's what we see here written down below. Notice that we have m omega over h bar instead of 2h bar. Clearly here, after I simplified the exponential, I had to distribute them to both of these integrals, which is why we see them split open like this. We break them apart, that way we can go back to the table in the book and evaluate them in a one-to-one manner. All these constants up front stay put. We get them nice and simplified. The 1/4 plus the 1/4 gives us to a 1/2. This 2m omega over h bar came from this distribution. Again, constants, leave it out front. And we see what we have here. Again, since we have an even times an even, we can double the integral and change this negative infinity to a 0, and then we could form match it with the tables in the book, or you could use another online calculator. There's plenty of options. Here, again, even, because constant times this Gaussian, well, quite frankly, we've seen this 100 times already. So we should be familiar with this integral and the techniques to use to solve it. Once there, now we just clean up these forward constants one more time by tucking that 2 into the 1/2 power. 1/2 power and square root, same thing. And we see here that the result of this integral gives us a factor of h bar over 2m omega, which cancels with the original factor there. And so I use the red lines here to indicate that those two cancel. Once those two cancel out, and we see that we're just left with the factor of 1 in front, that leaves us with the square root of pi h bar over m omega, which is the same thing as this second integral yields here. So those two things cancel to 0 as well. So those two things cancel to 0. And the fact that we have a 0 in the bracket, this constant times a 0 yields to 0. And so we proved via the integral by explicit integration and the integral definition that when the two indices don't match, we get 0. Therefore, they're orthogonal. And we proved once again how valuable these solution sets are. So, until next time. Happy learning.